Good day and welcome to my YouTube channel. I am Arthur Francis Deban. Today we're going to be carrying out a review in volumetric analysis calculations and the formulas therein. So I'm going to cover the essential areas which we have touched all the while. We've done calculations in water of crystallization, percentage purity, redox, and all of that. So I'm trying to capture one video that contains all of those things in one place so that you can get a full package in a view in just one video. So far, we have been able to discuss about the formulas, the volumetric analysis formulas, which without them, we cannot do quite well in our calculations. So it is important that we should remember our formulas, that also be able to apply them. If you remember your change in subject of formula in mathematics, so we do change of subject, you're looking for the concentration of the acid, or the volume of the acid, or the number of moles of that, whatever you're looking for, you can easily make change of subject and get that which you need. So mathematics tends to be an integral part of chemistry, you should know that. So let's begin with the formulas, a review on the formulas first before we can apply certain other calculations. So we're going to start with calculation, the molar concentration, all right? So let me call it concentration. So we're going to talk about concentration in mole per dm cube and concentration in GDM which is the molar concentration and the mass concentration. Those are the two types of concentration we have. So let's begin with that. So this is molar concentration, 1. This is what we're looking for. So now we're going to look at the possible formulas which we can use. All the formulas that have to do with molar concentration. So any question that tends to deal with molar concentration, what are the formulas that we can use to apply in terms of solving it? So through that, you can easily outline the formulas and know the one that is nearest to what is given to you, probably, that you can use that to solve. So let's start with our first general formula, which we call it the CA, VA, CB, VB is equals to NA over NB. So this is the first formula. Here is CA, concentration of the acid. Here is concentration of the base. So technically, you may be looking for this or this whenever you're using this formula. So, and make the subject of whatever you want to. All right. Where then? Let's look at what does all these things mean. CA is concentration. I'll write it in short, of acid in mole per dm cube. If or mole per dm cube. Yeah, it's either you write it in this way or this way. While VA is volume of acid in cm cube. NA is number of moles of acid. CB, con of base in mole per dm cube. VB, volume of base in cm cube. NB is number of moles of base. Now, the Na, number of moles of acid, and NB, number of moles of base, doesn't have a unit. So that is how that goes. So this is what these variables mean. So when we are dealing with normal calculations in acid-base titrations, we use this. But what if we are dealing with redox? redox titration, we begin to look at, instead of concentration of the acid, we'll look at the concentration of the oxidizing agent. So we'll call that COA VOA over C reducing agent RA V RA is equals to number of moles of oxidizing agent over number of moles of reducing agent. So these two formulas can be used. The same variable, this is in mole per dm³, the same. That's how everything goes. But now this is for redox calculations. In redox, we use this. We don't use Ca. That is for acid-base titration. For redox titration, we use COA, VOA, concentration of oxidizing agent, volume of oxidizing agent, concentration of reducing agent, volume of reducing agent, equals the number of moles of oxidizing agent over number of moles of reducing agent. You make the subject of whatever you need and you proceed. So this is the first, let me call that is A, in calculating our concentration. Alright, so another formula for concentration, let me take that. Now B, we say molar con, that's molar concentration in unit, which is mole per dm³, is equals to mass concentration in GDM³ over relative molecular mass in G mole. So this is it. This is another formula for calculating molar concentration. So it depends on the variable given, you will know which one to apply. Alright? So if I have the mass concentration of the acid or the base, and the compound, the structure, maybe the acid is HCl, from there I can get my relative molecular mass, then I can apply this one. But when I have, in the other way around, the volume of the acid, the number of moles, the equation, I can deduce every other thing from there. So that is how the formula goes too. So let's look at the third formula for molar concentration. This is C. Okay. This is amount in mole over volume in dm³. Okay, so this is mole per dm³ for the third formula for what? Molar concentration. So that is how we go. Now, we're done with the molar concentration with the various formulas which you can use to deduce the molar concentration. So let's look at mass concentration. What are the formulas that we can use? This is mass concentration in GDM³. A for mass concentration. We say mass con in GDM³ is equals to molar con in mole per dm³ times relative molecular mass in G mole. So this is it. This is our first formula for mass concentration. So we say mass con is equal to molar con in mole per dm³ times relative molecular mass. So if you multiply these two, if the formula for mass con is in GDM³, now this is G mole. Let's be clean. Mole and mole will go out. According to indices, you should remember when number with equal bases are multiplied, the powers are added. So this is mole raised to the power 1 times mole raised to the power minus 1, which says we should add their power. So mole raised to the power 1 plus minus 1 give us mole raised to the power 1 plus times minus is minus, so I have 1. And 1 mole raised to the power, this is 0. Anything raised to the power 0 is 1. Then 1 times the GDN cube give you your GDN cube. So this is another way you just can, from there you know that you're right from the unit they're in. So we have our first formula for mass concentration. Let's look at the second one. Let's look at D. Mass concentration is mass in gram over volume in dm cube. So this is G dm cube, which is a unit here. So this is another formula which we can use when we are calculating the mass concentration. So with this, we're going to be fine. So let's move down to amount, perhaps. That's 3 now. The third one, amount. It's always in mole. A, amount in mole is equals to mass in gram over relative molecular mass in G mole. Grams will cancel gram. I'll be left with per mole. If I inverse it, I'll have mole for amount. That is for A. Let's see B. Amount in mole is equals to molar count in mole per dm cube times volume in dm cube. So if I strike this and this out, I'll be left with mole for amount. So this is another formula, another integral formula which we can use in our calculations. So this is, we are under amount. Let's look at formulas for relative molecular mass. For relative molecular mass. A, relative molecular mass in G mole is equals to mass concentration in GDM cube over molar concentration in mole per GM cube. So dm cube, this will go, this is G per mole, That's our first formula for that. Now let's take our second formula. B, relative molecular mass in G mole is equals to mass in gram over amount in mole. Let's see. This is G mole. Sorry, this is per mole. So this is gram per mole. So that's correct. That's our second formula for relative molecular mass. Okay, let's move on to formula for mass. This is 4. Let's look at the fifth formula. The fifth, which is mass in gram. A, mass in gram is equals to, from here, relative molecular mass in gmol times amount in mole. So mole would strike this out, I'll be left with this. B, mass in gram is equals to mass concentration in GDM cube times volume in dm cube. Now, dm cube, we'll take out dm cube, I'll be left with gram. That is another formula for mass. So here, we're trying to get all the various formulas that can be used when we are calculating, carrying out calculations in volumetric analysis, be it redox or whatever it is. And our fervent understanding of these formulas really will help us to move forward, to go faster. We don't have issues when it comes to solving, like you see when we get down to business of solving. But it is important or pertinent to know that without your fervent knowledge of these formulas, I don't see you surviving it. You're not going to go nowhere. So you must begin first by having the formulas in your head and understanding your basic indices application to check when you finish the formula to understand whether it is correct or not. For example, yeah, this is my gram, but this is dm cube. Gram times dm minus 3 dm raised to power 3. I understand from lots of indices that when numbers with equal bases are multiplied, their powers are added, this and that is added. So if I have dm minus 3 times dm raised to power 3, they have equal bases, I want to add their powers. So I now have dm raised to power minus 3 plus 3, minus 3 plus 3 is 0. So dm raised to power 0, and that is 1. 1 times g, which is gram, gives me gram. So my understanding of indices too will help. When you state out your formula with their various units, you'll be able to know whether you're right or wrong. There are high tendencies where we make mistakes. Yes, no, you cannot be too perfect or too careful. You know, as a spirit lead, sometimes you make mistakes, which is human. But if you have this knowledge to check whether you're correct, it will be better, because probably maybe in exams or something, you're just solving and you're time conscious, so you wouldn't be able to take all the time in the world to go back reflecting, but you just check here and you see that you're right and you move on. So we have the fifth one, and these are the basics formula. Let's proceed to, percentage purity. Percentage purity. Now, percentage purity is equals to the mass conc of pure sample over mass conc of impure sample times 100. That is the first one, A. So if that is true, we can now have percentage impurity, which is 100 minus percentage purity. This is B. Now, I know too well that for me to be able to get this, since there is a purity here, I must have to get my percentage purity first. So my impurity becomes 100 minus purity. That is good. You move on. So this is about percentage purity. Let's look at number of moles of water of crystallization. When you want to get the number of moles of water of crystallization, which is the X. So let's see how we do that. number of moles of crystallization. So we say, for us to be able to get a number of moles of water of crystallization, we say the mass comm of the hydrated salt or hydrated substance over the relative molecular mass of the hydrated tube. This is equals to the mass comm of anhydrous over relative molecular mass of the anhydrous. Now, these anhydrous and hydrated, these are salt or acid that contains water in them. There are certain salt that when you expose them to the atmosphere, they absorb so much water that they become a solution. While some, the hygroscopic will absorb a little, the deliquescent will absorb so much, and so on and so forth. So, if this is dehydrated, let me call it calcium triiodocarbonate 4.XH2O. The H2O, the X here, tell us the number of moles of water, which we don't know, that we are looking for. This is the X. And the relative molecular mass of the dehydrated becomes calcium triiodocarbonate 4. There will be no water. This is now, relative molecular mass of the hydrated, that becomes, this is 106. Calcium is 40 plus 12. Okay, let me just do it. 40 plus 12 plus 48 is 100. So this will be over 100. 100 here plus X18, which is this. And that becomes mass comm of the anhydrous. What am I doing? This is the mass comm. Pardon me, please. This is mass comm of hydrated, which could be anything. Let's take it to be 2 GDM cubed. And the relative molecular mass of hydrated, which is this. This is mass comm of the anhydrous. Anhydrous, let's say 1 GDM cubed over the relative molecular mass of the anhydrous will be just 100. And with this, we can now make X the subject. And now X becomes the number of moles of water of crystallization. When we impute it into the main formula, we know the number of moles. Is it heptahydrate, which is 7? Is it decahydrate, which is 10, trihydrate, and so on? So, this is for number of moles of water of crystallization. What about percentage of water of crystallization? So, let's take another one, percentage of water of crystallization. Now, the 9th formula, percentage of water of crystallization. Okay, this is the percentage of water of crystallization. We want to look at the percentage now. So that's because if the substance is this, dot XH2O. So if this is the substance, the compound which we are having, and this is the hydrated compound, and now I want to look for the percentage of water. So we take the product of water, the amount of water, which is SH2O, over the entire compound, which is Na2CO3.XH2O, times 100. This becomes the percentage. Whatever it is, that is your answer, becomes your percentage. So our focus right now is to be able to elucidate all this, the formulas therein in volumetric analysis, both redox and acid-base, and also see how we can apply them in terms of that reaction. So I think with this, we've been able to cover all the essential formulas. So now we'll go into the calculations and see for ourselves how we can make use of those formulas to solve certain other questions. It's very important. But don't forget that when you forget the formula, everything is gone. The centrality of the message is first, have the formula. When you have the formula, it becomes easier for you to deal with it. I'll show you why we'll proceed further. So let's start taking questions. So let's say our first question. A is 0.125 mole per dmq H2SO4. B is a solution containing X GDM³ of sodium hydroxide. So there is a way in which we're going to deal with this. We're going to have A and B. A will be for acid. So this is my acid, and B will be my base. So I will state out the given variables under acid and base, so that when I am seeing what is given to me, I will be able to easily determine the formula to use. It is as simple as that. So in calculations, it is important if you can state out your given variables first. Then from there, you can easily look at the given variables and now determine the formula to be used. A whole lot of formulas. So let's go in that pattern. We say A is 0.125 mole per dmq H2SO4. So this is A, which is H2SO4. And that's the concentration of the acid is 0.125 mole per dmq. Okay. B is a solution containing X GDM³. B contains X GDM³. We know the unit here, GDM³, is for mass concentration. So they are asking, what is the mass concentration? That X GDM³ means unknown mass concentration, which they may likely ask us to find the X so that it will be known. Let's proceed. GDM³ or sodium hydroxide. So here is sodium hydroxide. Put the acid into the burette and titrate against 20 or 25 cm³ portions of B. So let's use 25. Volume of the base is 25 cm³ of B. Using methyl orange as indicator, record the volume of your pipette. Tabulate your burette readings and calculate the average volume of acid used. So we're going to now find out from our titration what is the volume of acid. So from the titration calculations here is 23 cm³, which is 23.0 cm³. So this is what we have. Now, the equation for the reaction involved in the titration is they've given us the equation of reaction. So we should calculate the amount and all that. So let's get our equation of reaction so that we'll be able to know the number of moles of acid and number of moles of base. So my Na and my Nb can be gotten especially from the equation of reaction, which is H2SO4 plus sodium hydroxide, which is sodium sulfate plus water. So we check if it is balanced. We have 2 hydrogen here plus 1, 3, and here we have 2. So if I add 2 here, my hydrogen becomes 4, and I add 2 here, my hydrogen becomes 4. That's 2 plus 2, 4, therefore. Now sodium is 2 here, so sodium is 2. Remember, this is aqueous, and liquid. So from here, number of moles of acid is 1, number of moles of base is 2. So from here we can now proceed to calculate whatever they want us to calculate. So let me take the formula out so that we can start with the solutions. Number 1, let's say amount in mole. First question says, calculate amount of H2SO4 in the average volume of acid used. The amount of the acid, amount in mole of H2SO4. Now, we have formulas for amount. We say amount is mass over relative molecular mass. You come here, look, they are talking of acid. Is there any mass given? there is no mass, but although there is a relative molecular mass which we can get from here, but there is no mass, so that formula is out. Come inside, come and sit down if you want to. So that formula is out. Then the other formula for amount is molar comm times volume. Now there is a molar comm here given and the volume here is given, which means you put your phone on silent, no noise. Whoever comes in here, tell the person I'm having a class. Okay? If the person wants to come in, can come in and stay quietly. Just listen, write if you want to. Okay? So, in that second sense, therefore, we will be using the second formula, which is amount is molar comm times volume. So let's see, amount of this is equal to molar comm of A times volume of A in dm3. The volume is always in dm3. So this is, the molar comm of A is 0.125 mole per dm3 times the volume is 23 over 1000 or dm3. I'm going to explain this. Now the volume given here is 23, but since the unit here is in cm cube, we want to convert the cm cube to dm cube, means you divide it by 1000. So that is how we get here now, in 1000. So let's proceed. We have our 0.125 mole per dm cube times, let's see, 23 divided by 1000, we have 0.023 dm cube. We know that this and this will go. This and this will go. What is left is in mole. So this become 0.125 times 0.023 is 0.00288 mole. So this becomes our answer. Now let us look at the second one, concentration of B in mole per dm cube. So if you look here, you see that the base, the concentration of the base is not given in mole per dm cube. That is what we are required to do. So we begin to also look at the various formulas which we can use, okay? Now, if we want to use the CAVA formula, we have the concentration of the acid, the concentration of the base we don't know, which means that that would be, that would be our unknown, what we are looking for. That would be what we're going to use or make the subject of formula. The volume of the acid is there, volume of the base is there, number of moles of acid, number of moles of base, which means the best formula to use in getting the concentration of the base is the CAVA formula. So let's see how we go about that. B, comm of B in mole per dm cube. For us to do this, we use the formula CAVA over CBVB is equals to NA over NB. This is equals to, if I make my this. Now the CB which I'm looking for is equals to, make this the subject, I have my CAVA NB over VB NA. And this is equals to, concentration of the acid is 0.125, so I have 0.125 mole per dm cube times volume of the acid is 23 cm cube times number of moles of the base NB is 2. Okay, let me be certain that we're doing the right thing here. Now CD is CAVANB. CAVANB, okay, over VBNA. Alright, we're good. Now, this is over VB, volume of the base is 25 times 1. And that is equals to this. Oh man. We have 0.125 times 23 times 2 divided by 25, which is equals to 0.23. So our concentration of the base is straight 0.23. So now I can take it to be 0.23 mole per dm cube. Now this is the concentration of the base from what we have gotten here so far. So the next question will be value of x. Okay. Now when I was talking earlier on, I made mention of the fact that the x that is given to us is not known. So they may likely ask us to calculate the value of that x, like just came up right now, that we should find the value of x. Now, what is the value of x? It is the mass concentration of the base. Simple as that. The mass concentration of the base. So what is the mass concentration? What are the formulas which we can use to get the mass concentration of the base? We say mass concentration, we have the first formula, which is mass or in gram over volume in dm cube, which is not it. We can't use that because we do not have mass here in gram. And the volume, of course, we can convert that to dm cube, but we do not have, so we can't use that. We also have another formula for mass concentration, which is the molar count times the relative molecular mass. The molar count of the base, we just calculated it now, which is 0.23 mole per dm cube. That is it. So the second formula is molar count times relative molecular mass, and we can calculate our relative molecular mass here, which means that is the formula we're going to use. So our diverse knowledge of the various volumetric analysis formulas will really help. When you state the first one, you check whether it can be used. If it cannot be used, you check the second one and the third if there is. And so we move. So let's see what we do then. Now, the third question says, calculate the value of x. Now, for us to get the value of x, which we understand that is the mass concentration of the base, then we say mass con of B is equals to molar con of B times relative molecular mass of B. And the molar count of B is 0.23 mole per dm cube times the relative molecular mass of this is sodium hydroxide is 40. This is 23 plus oxygen is 16 plus hydrogen is 1. That is 40. So now I have my 40 G mole. And this is equals to, when I have multiplied my 0.23 times 40 will give me 9.2. So 9.2 GDN cube. Alright, the mole will go with the other mole. I'm left with GDN cube. So that is it. So with this, we have just calculated our first question and we're done with it. So we can take our next question. Okay. Let me explain the board so that we can take the next one. A is a solution of KMnO4, that is potassium tetraoxomanganate 7. B is 0.02 mole per dm cube of ethane dioic acid, and solution C is 1.0 mole per dm cube of concentrated H2SO4. If 25 cm cube of solution B gives 16.5 of A for complete oxidation, from the equation of reaction below, they've given us a equation of reaction, we should calculate the concentration of solution A in mole per dm cube, concentration of solution B in GDM cube, and amount of A in the average volume of acid used. So let's see how that works. Yeah, so I'm still going to list out the given variables for the acid and the base as the case may be. So I have my A for acid and B for base. So, okay, let me not say A. It's not A, it's oxidizing and reducing agent. So here is O for oxidizing agent, here is R for reducing agent. So let's proceed. Here is KNNO4. Here is H2C2O4, ethane dioxide acid. And this is 3. Okay, now let's bring out the variables. B is 0.02. The concentration of the reducing agent is 0.02 mole per dm cube of ethane dioxide acid, and solution C, which is the acid, we have to acidify it before. Now, if 25 of solution B, so the volume of the reducing agent is 25 cm cube. If 25 of B gives 16.5 of A, now volume of oxidizing agent is 16.5 cm cube of A. You call it that way. Okay. For complete oxidation, from the equation of reaction below, alright, they've given us equation of reaction which we are going to use to know our NN, number of moles of another. 2 MnO4 minus plus 5 C2O4 2 minus plus 16 hydrogen plus gives us 2 Mn2 plus 10 CO2 plus 8 H2O. How to balance this? I have a video on this on how to balance your redox. So it is important you know how to do that. Because if this question were to be an exam question, this may not be balanced. So you will be required to balance it. So let's see. Now, number of moles of oxidizing agent is 2. And the number of moles of reducing agent is 5. Concentration of oxidizing agent is unknown. So from here, let's see what they want us to do. First question. Concentration of solution A in mole per dm cube. A, which is the oxidizing agent. The concentration of A in mole per dm cube. So let's start. I'm going to take this out. So, first question, count of oxidizing agent in mole per dm cube. So, in mole per dm cube, we are going to apply the formula like I introduced here earlier on from the beginning. One of the formulas, which is the COA, BOA. So let's see how that one works. Concentration of oxidizing agent times the volume of oxidizing agent over concentration of reducing agent times the volume of reducing agent is equal to the number of moles of oxidizing agent over the number of moles of reducing agent. And this is equals to, I'm looking for the concentration of what? Oxidizing agent. So my COA is equals to, now, concentration of reducing agent times the volume of reducing agent times number of moles of oxidizing agent over volume of oxidizing agent, times number of moles of reducing agent. So for me to do this, I have this NRA. Concentration of, okay, this is what I'm looking for. Sorry. This is what I'm looking for. So I have CRA, VRA, NOA over VOA, NRA. This is it. So now let's apply and see what we get. Now concentration of the reducing agent is given to be 0.02 mole per dm cube times volume of reducing agent VRA is 25 cm cube times number of moles of oxidizing agent NOA is 2. This is equals to volume of oxidizing agent VOA 16.5 cm cube times number of moles of reducing agent is 5. So this is equals to, now we check it out, we have 0.02 times 50, divided by 16.5 divided by 5, 0.0121. This is 0.0121. Am I right? 0.0121 mole per dm cube. So this is the concentration of the oxidizing agent. That of reducing agent is 0.02. This other one is 0.01. So let's take our next question. We're now going to look at the concentration of solution B in GDN cube. This is our B. Let me put the value for this. This is 0.0121 mole per dm cube. Now we are asked to calculate the concentration of solution B in GDN cube, which is B in GDN cube. So GDN cube means the mass concentration. Now, what are the formulas for mass concentration? Mass concentration is molar conc times relative molecular mass. Yeah. So this is my relative molecular mass. I can get it from here. I think that is 90. And the molar conc is here. So I can easily do that. So now let's do that and see. B, question B. Conc in GDN cube of B is equals to the molar conc times the relative molecular mass. The molar conc is given to be 0.02 mole per dm cube times the relative molecular mass is 90 g mole. Now, how do we do that? H2C2O4. Now, this is 2 plus carbon is 12. That's 24. Oxygen is 16. That is 64. 88. 90. So, that is it. Let's see what we have. 0.02 times 90 is equals to 1.8. So the mass concentration, 1.8 GDN cube of B or R, reducing agent. So we've gotten that. What's the next thing? Amount of A in the average volume of A used. The formula for amount is molar conc times the volume in dm cube. So we can get that. So let's see. To see amount of A in bracket oxidizing agent is equals to molar count of A, okay, amount is molar count times volume, alright, times volume in DNQ. So this will become, the molar count is 0.0121 mole per DNQ times the volume of this is 16.5. 16.5 divided by 1000, 0.0165. 0.0165 DNQ. And this is equals to, if I multiply that, let's see what we get. We have 0.0121 times 0.0165 is equals to, the amount is 0.000199. Let's look at that. So this is our amount in mole. We take another question. So what I'm trying to do today is for you to see how we can solve redox question and normal acid-base questions. I think I've solved one. Let's take more and see how we can diversify and move. Our next question says that A is a solution containing 3.70 GDN cube of an acid H2X. B contains 2.15 of sodium hydroxide per 250 cm cube of solution. We should put A in a burette and titrate it against 20 and so on and so forth. So let's be writing the variables down. So we always have our A and our B. Alright, that is A and B. We say A is a solution containing 3.70 GDM cube of H2X. This is H2X, that's the acid. A is GDN cube is equals to, the GDN cube is 3.70, 70 GDN cube. What does that mean? That the GDN cube is 3.70 means the mass concentration of the acid is 3.70. Let's take B a little bit out. So here is my B. We say that B contains 2.15 grams of sodium hydroxide. It contains what? 2.15 gram in 500 cm. Oh, sorry, in 250 cm cube, not 500. In 250 cm cube. Okay, of solution. Put A into the burette and titrate it against 25 portions of B. So volume of the base is 25 cm cube. 5 cm cube of B. Using methyl orange or screen methyl orange as indicator. Record the volume of your pipette, tabulate your burette readings and calculate the average volume of A used. And the average volume of A is 26.6. So the volume of acid is 26.6 cm cube. Okay. Now, from the result and information provided, calculate 1. The concentration of solution B in mole per DNQ. Okay, that's the first one. Or B in mole per DNQ. Now, from the variables given, let's look at them. We want to calculate the concentration of B in mole per dm cube, molar concentration. So when you look at, this is B, all the variables given on B are this. So now let's see, how can we calculate the molar concentration from what we are having here? That becomes the next thing, our ability to think. Now we begin to check what are the formulas for molar concentration. We have the CAVA, okay, that one is out. We have that of molar concentration was mass con over relative molecular mass. Okay, that we can use. We also have the other one, which is amount over volume. Amount is not here, but though we have volume. In short, they are true volumes. So that one is also out. So now we are going to use that one which says molar concentration is equal to mass concentration over relative molecular mass. The relative molecular mass can be gotten from here, which is 40. But what about the mass concentration? For you to get the mass concentration, remember that mass concentration is mass over volume. This is mass over volume given. So from here, we can get our mass concentration. Then we apply the other formula, which is mass con over relative molecular mass, and that will serve. So for us to be able to proceed, first we calculate the mass concentration of B. So let's start. It is not, they didn't ask us, but that is the basic thing to be done first. So 1, mass con of B in GdN cube is equals to mass of B in gram over volume of B in dm cube. So the formula says mass over volume in dm cube. So this mass is here, volume is there, so we can proceed. And this is equal to, the mass is 2.15 gram over the volume is 250 over 1000 in dm cube. And this is equal to, what do we have here? 250 divided by 1000, sorry, 10 is missing. It's equal to 0.25. So I have 2.15 in gram over 0.25 dm cube. And that is equals to what? 2.15 divided by 0.25 is equal to 8.6. So this is 8.60 GdN cube. So now the GdN cube of B is equal to 8.60 GdN cube. This other one, the GdN cube is 3. So we've gotten the first thing there. Now, they didn't ask us, but that is what we should do first. So we have done that. Now, let's go to the main question of the day. The main question says that we should calculate the molar concentration. Molar concentration of the, of the base, which is 1. Molar con of B is equal to mass con of B over the relative molecular mass of B. So from here, we're able to understand that the mass concentration can only be gotten, although it wasn't given, but we understand that we can actually derive that, which we have done. And the formula for molar concentration, which is mass con over relative molecular mass, now we'll apply. So our mass con, we just got that to be 8.6. So I can easily have my 8.60 GdN cube for the mass concentration over the relative molecular mass of sodium hydroxide is 40 G mole. Now, how do we get the 40? This is sodium hydroxide. Sodium is 23 plus oxygen is 16, plus hydrogen is 1, and that gives us 40. So if that is true, we can now have our molar count to be 8.6 divided by 40, 0.215. This is 0.215 mole per dnq. So we've been able to get our concentration of the base to be 0.215 mole per dnq. Now, what is the next question? Okay. It says concentration of B in mole per dnq. Okay, we have done that. So the last one here is the value of X. Oh, there's value of X here too. Okay, for us to know the value of X, it means we must know the relative molecular mass of this guy. But let's see how that works. Now we have H2X is equal to the relative molecular mass. This is a standard. So for us to be able to get the value of X, it means that we must have to calculate the relative molecular mass, which we don't know at first, so we cannot even go there. So then, how are we going to get here? We have to go down. We have this. We can now proceed to have our molar concentration. Remember, we have molar com, or let me call it GDMQ, equals to molar com times relative molecular mass. I have GDMQ. I have to calculate my molar concentration here. If I get my molar concentration, then I can get my relative molecular mass. So without the molar concentration, I cannot get this. And if I get this, that's when I bring it back into this formula and get my X from here. So I still have a long way to go right now because I have to check how to do that. So let's go back. The dexterity is rugged, but we are going to get there. So we're going to use, since we've known our concentration of the base, we're going to use the CAVA formula to get the CA so that we can now proceed to get our RMM, which is the relative molecular mass, after which we bring it here. So let's proceed. We have my CAVA over CBVB is equals to NA over NB. I'm looking for the concentration of the acid right now. So I have my CA would be CBVBNA over VANB. So this is what I have. But then, what is the number of moles of acid and number of moles of base? Means the equation of reaction must be balanced. So I come back here, I have H2X plus sodium hydroxide. This will give me sodium X plus water. Now, let's check if it is balanced. If it is not, we balance it. We have 2 hydrogen here plus 1 hydrogen, that's 3. Then we have 2. If I put 2 here, I will have 4 hydrogen. I put 2 here, I have 2 plus 2, 4. So my hydrogen is balanced. Now sodium is now 2. I put 2 here, I now have 2 sodium, 2. So from there, the equation is balanced. So the number of moles of acid, Na, will now become 1, and my NB will become 2. So the formula now, I can proceed. And I have concentration of the base, which is 0.215 mole per dnq, times volume of the base, which is 25 cm3, times number of moles of acid, which is 1, over volume of the acid, which is 26.6 cm3, times number of moles of the base, which is 2. So from here, the concentration of acid, Ca, will become this. So let's see what we get. 0.215 times 25, okay, divided by 26.6 0.6 and 2, which is 0.1010. So this is 0.101 mole per dm cube. So this is my molar concentration. Now I have 0.101 mole per dm cube. Now, if that is true, I have my molar con now. So I can easily get my relative molecular mass so that I can use this formula. So all this we are doing is just to apply this formula. So let's see how that goes. My GDM cube onset was given to be 3.70 is equals to, the molar con is given to be, which I just did now, 0.101 times my relative molecular mass. So my relative molecular mass will therefore become 3.7 divided by 0.101, which is equals to this. So when I do that, let's see what we have. 3.7 divided by 0.101. This is equals to 36.6. I have 36.6 G mole. That's not all yet. Now we can now apply the main formula to finish. So we have 36.6 G mole. Let us now get the value of X. To get the value of X now, let's come this way. Okay, for the value of X, I have H2X is equals to 36.6. Hydrogen here is 1 times 2 plus X is equals to 36.6. My X is equals to 36.6. This is 2 minus 2. My X is equals to 34.6. Approximately, X is equals to 35, approximately. So, that is my value of X. So, we're going to take another question. A question here says that 0.019 KMnO4 react with 6.0 GDM cube of impure ethane dioxide acid solution. 25 of ethane dioxide acid react with 23.5 of KMnO4. If the equation of reaction is given to be this, so we need the equation of reaction is quite essential. We should calculate the percentage impurity of ethane dioxide acid. It looks simple, but there are over 3 steps. They skip, they didn't tell us. So from our own knowledge, we'll know what to do when we get there. So now let's begin. We have our oxidizing agent, so I call it O. O and the reducing agent, R. We say 0.019 KMnO4, so the oxidizing agent is KMnO4. Potassium tetraoxomanganate 7. Okay, and the value therein is the concentration of oxidizing agent is given to be 0.019 mole per dm cube. Our reducing agent here is ethane dioxide acid, C2O4. It's ethane dioxide acid. So we say 0.019 KMnO4 react with 6.0 gram of impure. So this is 6.0 gram of impure base. So we are having the mass concentration dm cube of impure salt or impure acid, as the case may be. So in percentage purity, we deal with the mass count of pure and mass count of impure. And we say now that with 6.0 is the mass concentration of the impure, as given to us. Let's see where they are going. Of impure ethane dioxide acid. 25 of ethane dioxide acid, which is the volume of the reducing agent, is 25 cm cube. React with 23.5 of KMnO4. Volume of oxidizing agent is 23.5 cm cube. If the equation of reaction is this, so they always give the equation of reaction, but if they do not, you balance it yourself. We have 2 MnO4 minus plus 5 C2O4 2 minus plus 4 hydrogen plus gives us 2 Mn2 plus 10 CO2 plus 8 H2O. So from here, we have the number of moles of oxidizing agent here to be 2. And the number of moles of reducing agent here to be 5. So I think that is all. 0.019, okay, given 6 this of impure, 25 of ethane dioxide we have with this. If the equation of reaction is given, blah blah blah, calculate the percentage impurity of ethane dioxide. So straight up, let's just go straight up to percentage impurity. Remember, I said formula for the percentage impurity is equal to 100 minus percentage purity. Which means that we must have to know what is our percentage purity. And the percentage purity, the formula says, mass ton of pure ethane dioxide over mass ton of impure ethane dioxide times 100. So we have to deal with this first before we come back here. Now, what is given to us here is the mass ton of the impure ethane dioxide. How are we going to calculate the mass ton of the pure ethane dioxide? For us to do that, we use our formula mass concentration, which is GDM cube. That's the mass ton equals to molar ton times relative molecular mass. So we must know the molar ton of the ethane dioxide. We know the relative molecular mass to be 90 if we have to calculate that. So that by that we get our mass ton of the pure. After that, before we can apply it in this formula. So let's begin with the calculation. I'm going to take this on out. So from here, I want to get the molar concentration of the ethane dioxide so that I can get the mass concentration of ethane dioxide, which is non-pure. Then I can now proceed to get that one. So the first thing is molar ton of R1. Molar ton of R, which is the reducing agent, ethane dioxide. For us to get the molar ton of that, the various formula, we have the CVA formula, we also have that which is mass ton over relative molecular mass, we also have that which is amount over volume. So if you look at those three formulas, the only one, the most suitable one to be used is that of the COA-VOA. That we can deduce from what is given here so we can proceed further. So let's see that. We have the concentration of the oxidizing agent times the volume of oxidizing agent over concentration of reducing agent times the volume of reducing agent is equal to the number of moles of oxidizing agent over the number of moles of the reducing agent. So from here, I'm looking for the concentration of the reducing agent, which is the CRA, will therefore become the concentration COA times VOA times NRA, all over the VRA times the NOA. So this is equals to The concentration of the oxidizing agent is given to be 0.019. 0.019 times, I'm not going to put a unit again because my markers are almost going. So volume of the oxidizing agent is 23.5. 23.5 times number of moles of reducing agent is 5 times 5 all over the volume of the reducing agent volume of, okay, that's 25 times number of moles of oxidizing agent is 2, that is 2. So this is equals to, so check that with the calculator. I have 0.019 times 23.5 times 5 equals to this, divide by 50. 0.0447. So this gives me 0.0447 mole per dm³. So now I have my concentration of the reducing agent to be 0.0447 mole per dm³. Okay, if that is it, we are going to get the percentage purity. So now we have to get a mass count. We've gotten this. We have to now use this to get a mass count of the pure ethane dioxide. What is given is the impure. So let's see that. 2. Mass count of pure ethane dioxide. Mass count of pure R. This is equals to the molar count, times the relative molecular mass, So this is equals to 0.0447 times the relative molecular mass is 90. So this is equals to 0.0447 times 90 is equals to 4.023 GDM³ of pure R. Remember, some time ago I said earlier on, the mass concentration of the impure must be higher than that of impure. So whenever you do your calculations and that of pure tends to be higher, means you're wrong. So like you can see here, this one is given, which is 6. The one we calculated is 4. It tends to tell you that we're on track. So now we've gotten the mass concentration of the what? Pure. And we have that of impure. So now we have to calculate first our percentage purity. Then, before we can answer their question. So now let's go. The top one is percentage purity. Okay. Now, percentage purity, I said, is the mass count of pure, which is 4.023, over the mass count of impure, which is 6.0 times 100. And this is equals to 4.023 divided by 6 times 100. Is 67.05. 67.05%. So it's 67.05% pure. The ethane dioxide at least is above 50, so that's not bad. So the final question, which is the main question they're asking us right now, they say what is the percentage impurity? So now is the time for us to calculate what they are asking us. So we see how we've gone in a roundabout manner trying to get to their destination. All these things we've done, they never asked us to do them, but we should understand from the basic principles of calculations that you cannot get your percentage impurity without knowing the mass concentration of the pure, without knowing the molar concentration of the same ethane dioxide, without knowing the percentage purity. All these steps are there. So it may look simple when you look at it from the onset, but all these steps are there. But once you miss any one, you're out of the game. So now finally, let's see what it is, the percentage impurity. So finally, we say percentage impurity is equal to 100 minus percentage purity, which is equal to 100 minus 67.05%, which is, okay, minus 100 minus 32.95. This is 32.95%. So the impure rate of the whole thing is 32.95. So it means the percentage, the purity status was very high, and that's not a bad one. So we've done justice to the essential areas which I think are important that we should know. We have looked at the formulas, the acid-base titrational formula and that of the redox, and we have seen how we can apply them in all ramifications, especially whenever we are required to. And we understand intrinsically that you cannot do any of these calculations if you do not have all those formulas in your head. There are more than 15 formulas if you want to count them. They must all be in your head so that you'll be able to apply them when required. So we're going to stop here for the day and continue any other time we meet again. But don't forget to subscribe, press the like button, and the notification bell. So whenever any video is being uploaded, you'll be able to get the notification. Do have a wonderful time. I see you again when I see you.